a session on that focus on AI and agents embedded in the real world. So I think this will be a very interesting session in which we have 3 talks. The first one is by Giovanni De Toni from Fondazione Bruno Kessler, University of Trento. So Giovanni, you have 20 minutes.
Okay, so good morning everyone. I guess you can all hear me. Today we're talking about mostly collaborating and let's say contesting AI, AI applications, and the research we'll be doing about these 2 topics. So most of us have seen, let's say, the tremendous impact of AI in our society, in many fields, decision making, medicine, etc. But there are also, let's say, we've seen also like potential bad effects of AI in the context of, let's say, fairness, in the context of bias, especially in, again, decision making applications. And that show that's how we should like tread carefully with these technologies in general. And I usually like to start with an example about what I mean by all of this, by bias and unfairness. Imagine that there is like this Alice who's trying to apply for a loan at their hometown bank. And the bank uses a very good black box model to understand, let's say, if Alice is worthy to be granted the loan or not. And as it works, Alice sends her application through the system, and the decision-making model, AI-based model of the bank, answers by telling Alice, okay, actually we cannot really grant your loan application because of some reason, because of the system decided that you are not worthy to get, you are not trustworthy enough to get, let's say, your loan application granted. And unfortunately, Alice usually has no real mean to understand why the decision was given and let's say how to possibly improve to be granted a loan eventually. Funnily enough, why fictitious this example is not that fictitious, because there are in the news there have been examples of, for example, people being rejected like from mortgage application because of let's say AI system used by for example the financial institution. For example, this is like an example of Crystal and Esquias from the US. So this is actually something that can happen and happens nowadays. In the past years, because of these issues, there have been many laws have been, let's say, developed and studied. For example, the AI Act, the GDPR, the California Consumer Protection Act, I think, that should, let's say, prevent or like protect like users, final users, from this harmful behavior of these systems. And one safeguard that gained traction in the past years, which is most interesting, is called algorithmic contestability, which basically is the idea that we as people should be able, let's say, to contest and, let's say, have the means to challenge the decision taken by decision systems. Okay, but in as many laws, they don't really define how can we operationalize this kind of notion of contestability. And we look at this problem, let's say, with the eyes of machine learning researchers. So, you know, in my research and our research, we try to, let's say, provide a feasible path towards contestability by using actionable explanations. To provide actionable explanations to people in order to let them know how to understand why they were given a certain decision and how to act in order to improve their outcome, for example. In the case of the Alex example, that would be for giving, for example, a recourse recommendation that tells, okay, if you had increased your income by 3%, then we would have given you the loan in a counterfactual fashion. So in this presentation, what we mean by explanations in general, we mean, again, counterfactuals. And just to give you, let's say, a very brief walkthrough of what a counterfactual is. Imagine our standard scenario in machine learning where we have features and we have a target variable we want to predict. In this case, it's binary, so either you get the loan or not. Then imagine that we have a classifier which is approximating our, let's say, posterior distribution, let's say. Imagine also we are given a function, a distance function, a cost function that tells us how 2 individuals are like far apart, for example. And the all this problem about, let's say, contestability and general giving counterfactual explanations for these kind of scenarios boils down to solving these equations in which we want to find the minimal changes you have to do to your profile in order to get a different classification from the one that you were actually given in the first place. Pictorially speaking, this means that, for example, if we are classified, this is the decision boundary of classifier, if you are classified in the blue area, which might be, let's say, the bad area where we won't get our law application granted, we want to move to the red one. So through diverse potential paths, and like C, B, and D could be, for example, counterfactuals. So where you would end up, which are the changes you have to make to your profile in order to get, like, to the red area, which is the good one in this case. So in this, in the past years, let's say, we started to think about developing, let's say, a pipeline to operationalize, let's say, formally these notions. And we're going to cover in this quick presentation all these aspects. We believe that first we need to learn how to explain certain part of the model, decision of a model, geared towards, let's say, this context of contestability. Then we need to transform these explanations into recommendations in the form of tailoring them to the user needs, okay? And then there must be a step of, like, evaluation and deployments of these technologies to understand how to improve the first two steps, okay? And we, let's say, published several work about these topics. So the first part, we're gonna, like, see very, very briefly, is the idea that we need to find, let's say, counterfactuals given a black box model. Okay, we need to find, we need to solve the previous, find ways to solve the previous optimization problem. And in our research, we view this algorithm contestability task as a sequential decision-making task, in which the user has to take several actions in order to change the outcome of the classifier, and therefore we developed a method called FAIR, which incorporates a discrete search procedure and a reinforcement learning agent to learn, let's say, and amortize the global policy to generate counterfactuals actionable for, let's say, for users, where the actionability notion is described by our, let's say, our cost function, our distance function. Again, we evaluated this with, let's say, some, let's say, synthetic scenarios by looking at the validity, which means how many times our counterfactuals actually change the outcome of the classifier. And with respect to our other competitors' models that were available some years ago in the literature, okay, our approach is, okay, achieves, let's say, a very higher validity, let's say, and also since we are learning a policy, we are providing an amortized method that requires far less queries to the, let's say, underlying black box classifier of the bank, for example. Since most of the previous competitors were directly optimizing, solving that optimization problem for every user. Moving on, we then thought about, let's say, personalizing this kind of counterfactuals, because the idea is that maybe people, users, have different requirements and different preferences about which action they can actually perform. For example, you can imagine I'm able maybe to increase my salary by 3%, but some other person or people could be more. It could be easier for them, for example, to lower their debit, their monthly spending. Okay. So for this second part, we devised this. The first, let's say, human-in-the-loop algorithm to implement this kind of algorithmic contestability. And the idea is that we employ an interactive procedure in which we elicit user preferences in order to tailor the counterfactuals to your own profile. Okay, so they're not like general counterfactuals, but they are tailored to your preferences and to your actionability requirements. And to do so, again, we explored some techniques about, let's say, Bayesian inference and preference elicitation to account for example, uncertainty over the user answers and so on and so forth. To give you an example, this is kind of like the pipeline. So we show certain recourse recommendation or counterfactuals to users. The users picks the one that they prefer the most, and we keep like iterating this loop until we hit, let's say, a query budget. And again, like in some like simulation experiment, with realistic data, we saw that by interacting with users, we can actually get lower costs. I mean, counterfactuals that achieve the same validity, but which are considerably cheaper with respect to the other competitors, which do not incorporate the user within the counterfactual generation process. So once we have done the first two steps, we then thought about making all of these techniques, let's say, easily accessible from a user perspective. And therefore we focused on, let's say, we devised and created an interface where users can actually interact with this contestability algorithm in order to discover counterfactuals that can serve, for example, this interface, for example, could be given by the bank to tell the user, I can give you certain plans you can follow in order to be granted the loan on your next application. And again, in our scenario, we did, let's say, a small pilot study with simulated credit lending tasks, in which we evaluated the effectiveness of this kind of like guided style recurse interface, where the user is guided towards a counterfactual, versus a more exploratory interface, where the user actually has to find the counterfactual manually, without any help from the decision maker. And again, we get some results that, okay, people thought this this guided style paradigm was actually pretty useful, but they also enjoyed, for example, being able to discover counterfactuals manually by themselves. And so these results are could be very useful also to improve the first two steps, so learning to explain and the recommendation, because they tell us what actually user really needs. In the as the last part, one of the latest work, we instead thought about a more, let's say the robustness of over these counterfactuals over time, because when you deploy these techniques, you want these counterfactuals to be robust to user execution, but also to potential let's say trends. Okay, I'm going to explain more clearly. Basically, when you apply counterfactuals, when the users start to follow your counterfactual suggestion, it's going to take time for him to do that, because I cannot really increase or decrease my salary overnight. So I must be sure that between the point I give the counterfactual and when the user apply again, he must be still able to get a positive classification. Okay. So we, let's say, studied this task through the lens of causality, and the problem becomes, let's say, generating counterfactual for time series. So you can see on the graph on the left. So given that at time t we got our loan application rejected, what are the actions we should do to get our loan application accepted at time t plus whatever 2, 3, n? Okay. And in our latest research, we show that actually most of the counterfactuals methods for algorithmic contestability and recourse are not really robust to time. Okay, and they're pretty fragile, especially also robust counterfactuals are fragile to time. And let's say the only way, let's say, to solve this is to try to employ at least an estimator of the, let's say, stochastic process, or about how a user evolves in time. And which actually is also an important point to improve these methods before deploying them actually, let's say, in real life scenarios. So this first, let's say, very quick part about, let's say, contesting AI. We identify, let's say, several potential pitfalls of these methods anyway, or desiderata that are not satisfied. Usually, for example, counterfactuals are given ex post, the decision is taken. So if an unfair decision is taken, okay, the counterfactuals happens already when the decision is in place and is affecting, for example, a person. And in general, the problem that we have, for example, fairness or lack of accuracy, etc., sits within the decision support system itself. Okay, so counterfactuals and algorithmic instability is something that mitigated these issues, but it doesn't really solve it for good. So what we would like to achieve, apologize, what we would like to achieve is our, let's say, guarantees over these models. Okay, guarantees of accuracy or fairness, or in general that if we use a decision support system based on AI, it should complement, let's say, human expertise, provably in a way by design. So we shifted a bit in the last months or so, and we started to study how to design systems that complement human expertise, provably by design again. So consider like this very simple task in which I have decision support systems that helps a human expert decide, for example, a disease given an X-ray. Okay, and usually the decision support system we have now works more or less like this, where the system gives a prediction, or maybe gives also explanations, calibrations, scores, probabilities, etc., etc., and then the human expert has to factor in these informations to define, decide, make a decision. Okay, for example, maybe this guy has pneumonia. However, these systems implies that the human has to build a good sense of when to trust the system, okay, and how to incorporate the system prediction into the decision-making process, okay. And there are very conflicting studies about which are the tools, which are the things the system should provide, and which are the effect on the final prediction, okay. So there are, let's say, conflicting studies on which are the best, let's say, output that the decision support system should provide. We instead moved towards, and we studied a different kind of support systems that used something called prediction set, where instead of providing, let's say, explanations, probabilities, or calibration scores, etc., we output a set of predictions, okay? And the funny thing about this, the important thing about this prediction set, is that you can build them with coverage guarantees through uncertainty quantification techniques like conformal prediction. For example, we can say, I can give you a prediction set where the true label is contained within this prediction set with a bounded probability. Okay, so probability 1 minus alpha. And this is actually a theoretical guarantee. Okay. So in one of our latest work, we studied, let's say, how can we construct this prediction set in a way to maximize the human accuracy in the end, okay? Because we want to build these systems, this prediction set, in a way that the human benefits the most out of them. And this is represented by the problem on the bottom left side. Unfortunately, we found out that this problem is actually NP-hard and NP-hard to approximate, which means that there is no really, let's say, good solution that can work for all, let's say, all possible models, under the assumption of the human being represented by a multinomial logit model. But however, we found out that we can actually build a greedy algorithm that can give us performances which are, let's say, equal or greater than, let's say, conformal predictor. So we can actually build a system that complements human expertise, provably by design, in an efficient way. And we do, and let's say our algorithm works because we are able, let's say, to generate prediction set in which the labels inside confuse the least the human, okay? Because if in a prediction set there are, for example, two diseases which are very close, very similar, or where the human confounds them a lot, okay, then the human will not be able to, I mean, we might be confused by the outcome of our decision support system. Okay, that's mostly it. All of this research was possible thanks to like wonderful collaboration with a lot of people here. Some of them are here in the audience, here at the University of Trento and the Fondazione Bruno Kessler. And that's all from my side. Feel free to ask any questions.
Yeah. Questions? No question? Okay, so so when in the decision process you explained at the beginning, I guess there is a yes or no decision, right? So, but is always the case? I mean, usually we don't. Probably we need the support system that help us to take a decision, comparing different factors, and somehow may happen that also other parameter can be brought to the decision maker by the user itself, no, the client, in that case, that can somehow move the decision in one direction or the other. So I guess.
So one potential, let's say, we were like discussing with some like financial institution partners, let's say, and they told us that sometimes there is a loan officer that takes the decision in the end. Okay, so maybe mediated by certain systems or whatever. So there is a human actually in the end taking a decision, maybe helped by the decision support systems, and in that case, let's say a counterfactual would still be useful because it could, let's say, help the user maybe. Okay, like this is your profile. Okay, maybe you can implement a simulation system in which you say those tools. For example, that tells you, given this profile, maybe we won't give you the loan. We're not sure because then there is a human decided in the end. But if you were to improve your profile this way, then your chances to get the loan will improve. Okay, when you end up talking with the loan officer, with a human, okay, which will use my prediction.
But I think that it's possible to think a system that acquire new evidence from the client and actually may also change the outcome of the decision.
There is a very, let's say, understudied area which is called participatory classification, in which they try to do that. So the idea is that I want to create a set of, like, say, classifier with monotone accuracy in a way that the more information I give to you, the more, let's say, I will be correctly classified. Okay. But there is still, I think, nothing that works towards.
Because I was thinking that, especially in the domain, the medical domain, I mean, more evidence can be available when the decision has to be taken.
There is something that we're actually working on at the moment,
okay,
in which you can build this prediction set by. You need, for example, usually a physician arrives, I mean the patient arrives and he has no feature specified. And the physician can ask, for example, for exams, okay? And you need a way, let's say, to tell the physician, okay, you should do these exams in order to maximize your accuracy in the end, okay? Because if I tell you, the decision support system could tell to the physician, you should do these exams in a way to maximize the accuracy and to maximize your predictive accuracy on the disease that this guy will have. So it's kind of in direction.
Okay. Is there any other question, Giuseppe? Yes.
So,
wait.
So when you talk about counterfactuals, this is a very evocative term, but you know, the guy that didn't get the loan, you know, imagine if you get the answer, well, you just go and get a higher salary. Do you think this would be a valid solution to your algorithm?
I mean, most of these things.
So the issue basically is that when you frame the problem like you did mathematically, there is something missing, which is the set of valid solution for that individual. I mean, otherwise, it's not counterfactual. It's a nice mathematical problem.
Okay, usually the set of valid I mean, this is something that usually should be discussed with the stakeholders. For example, there are certain features which are not really actionable. So you should, like, say, avoid changing certain features because they are not, like, if I tell you should get younger to get your loan, it obviously is impossible, it's not actionable. And the second part about maybe increasing the salary is not valid for a specific user. This is something that we deal in the second, with like the second project, in which we have this interactive framework, in which a user can actually tell to the machine, look, for me it's very hard to change my salary because I don't really have the capacity now. So give me another explanations. I mean, this is something that actually don't really, maybe you can see it here, okay? But I mean, I don't really have it at the moment, but here, I mean, on the 3 boxes with the values, those are the counterfactors that tells you, oh, you should like do this or that. If you click in one of those in the interface, there is also, let's say, a slider that tells you how easy it is for you to do that, okay? So if you keep doing this, okay, in the end, like the system should understand, okay, you cannot really do that. I mean, this person is not able to change his income. So I need to find a different counterfactual with different actions, which might not exist also. That's another problem.
That's very likely. Also, I don't know if you've done any user study, but even if you expose a subset of solutions, that could have an impact on the workflow, because the person may be, for instance, let's say, insulted by the ones that you propose, so that it just stops right there. So that's when you go to the user side, okay? But I think, you know, thinking about having this other constraint.
Okay, Massimo.
I don't want to start a discussion, even if it's very, very interesting. But we have actually some results in the next talk, together with you.
This is not fair. Okay, anybody else? Okay, thanks Giovanni for the nice presentation. Now, Luigi, you want to come? Talking about AI in the real world, I think robotics, it's...
Okay, so I will talk today about embodied system, which is one of the areas where the FAIR project has delivered some of its results. In particular, it's the object of one work package inside the FAIR framework, whose overarching goal is to enable system to operate in the physical world, in particular in connection with robotic systems. So, what makes robots so special? Why should we devote a special attention to them? Well, the most evident nature of robots is, at least of contemporary robots, is that they operate in open environment. They have to respond to unexpected events, and they have to deal with the most unpredictable entity in the world, which are human beings. So this makes some difference with standard AI systems because they have, when you are developing an intelligent robot, you have to take into account such issues as safety, guaranteed level of safety, real-time responsiveness, explainability. Here in this case, explainability takes also a special meaning because people tend to distrust robots, right? So the fact that the behavior can or cannot be explained is something that really goes at the heart of their acceptability. And finally, last but not least, robots are supposed to live in a social world and abide by the same rules, written or unwritten, as we humans do. So given this context, our work has been developed along 2 different prongs. The first one is to develop a methodology of general applicability. And in this case, the methodology hinges on a mix of model-based and learning-based approaches, because they are both needed for reasons that will become apparent in a few minutes. It has to be flexible and evolvable, and at the same time it has to retain adequate level of explainability and safety, as I just said. And then what we also did is to put our methodology to the test of reality and try to confront ourselves with some concrete use cases, and some of them I will talk about later on in this talk. So let me start from the methodology. Now, consider a few motivation examples where our activities as humans typically unfold. Some of them managing a warehouse, building a complex, I don't know, in this case construction, applying a medical protocol, interacting with our humans. There are a few traits that these applications have in common. And the common characteristic is that the fact that we are able to execute this activity is based on a narrative. This narrative can be formal, like written documents, or informal, like observations, pieces of information that we collect during our life. We take this bunch of information, we take this narrative, and we transform it into knowledge base. This is a very computer science term, but a knowledge base means a place where this information is stored and becomes usable and actionable. And at times, as I say, the narrative can come from written reports, well-structured. Other times, these reports are not so well-structured, but the information is there nevertheless. It's just up to us to be able to extract it and make a sense of it. Okay, now let's move a little bit to robots. The big questions that we have dealt with in this methodology are, how can we generate and maintain a knowledge that we derive from this type of source? How can we make a good use of this knowledge? And then, in the future, how can we update the knowledge learning from experience? And what we are thinking of is a place where this knowledge is stored in a way that it's understandable to human, explainable, and it's also shareable and reusable for future purposes. Okay? So what we will look at in a few moments, and we will also like to have a scalability, of course. We will propose a framework where this knowledge is generated. It is transformed into planners, planning activity. And we can also leverage from our experience and learn from it. And finally, we can think of probabilistic and semi-probabilistic extension. This is a nutshell our workflow, the one that we have developed for this work. Our starting point is, as I said, a very narrative report. In this case, we have worked with natural language written reports that can be evaluated by a large language model and transformed into a knowledge base. This knowledge base is a logic knowledge base expressed in a logic language, a very famous one, Prolog. Then we also combine this high-level knowledge with a low-level knowledge that expresses what each and every resource that we have is able to execute. And we are able to do some consistency check prior to sending this technology into the real world in action. And then, based on that, we can generate a logical plan. In this logical plan, we can extract those elements that can be parallelized, and then we can optimize the execution of this plan with our resources, and finally generate what is called behavior tree, which is something that is amenable to execution. So this is a very toy example. You see, this is our narrative. On the left-hand side, we have a high-level description of our goal. On the right-hand side, we have a low-level description of the capabilities of our system that somehow refines them. Then we have a very nice button. We press it. And what we come up with is this knowledge base after a few iterations, because there could be cases in which there are inconsistencies, but I will skip this part. And then we come up with a knowledge base in which we describe our initial state, our goal, our actions. And then what we do is to also extract a low-level knowledge base in which we detail how our specific robotic systems is able to execute these high-level actions. And then what we do is that we generate a sequence of actions that we call a totally ordered plan, out of which we extract a partial ordered plan. So we single out those activities that are really supposed to be executed before each other, and others that can be parallelized, and then we implement and we produce a behavior tree. This behavior tree is directly executable. This short clip show, in this case, the narrative was just how to put two blocks one on top of the other, and this is what we did. And the entire flow was started from our narrative, and we came up with this execution of this thing. We have also worked on a probabilistic extension. In this case, we work in the same way. We create our knowledge base, but this time, instead of generating we generate a Markov decision process. And I would like to show you an interesting application of this. In this case, we have a human, and we are supposed to help the human. What we do is that we put some blocks in an order, and this order is supposed to nudge the human into executing its task, the castle, in this case, building castle, in a pre-specified order. So we would like to proceed layer by layer. We don't impose this thing, but what we do is that the way we arrange the blocks in the table, putting some closer, other farther from the humans, somehow induces this type of behavior. And finally, with 2 or 3 of my students, it worked. But this is interesting in its own respect, and we are still working on this. So there could be alternatives. Yes, we could generate directly the code, but in this case, the granularity of what we generate is too small for us to make a sense of it. We could generate PDDL instead of Prolog, but PDDL doesn't have the same ability of Prolog to reason about, make inference. And thereby, we have decided to have this intermediate abstraction layer where it's possible to include such things as the affordance of the objects and what is possible to do, etc., and make a pre-reasoning before moving on to the planning phase. Now let me move to another example. In this case, it doesn't have to do with the direct application of these techniques, but it's interesting nevertheless. In this case, the example is inspired to Industry 5.0. So we have a case where the robot and humans are supposed to work in close collaboration. So our problem is how to make this collaboration safe enough. What currently happens is that whenever a human comes too close to a robot, the robot slows down very much, and this can preserve the safety, but of course reduce productivity and have some price to pay. What we can do is to act proactively, make a prediction of what the human is going to do, and try to adjust the plan of our robot so that a situation where the robot is comes too close to the human and we have to slow down never happens. Okay? And how do we do this? We start from the video stream, we extract the skeleton, then we execute motion prediction. And we have experienced 2 different alternatives, one based on graphical neural networks and the other based on more standard regression of GMM. And then based on that, we move entirely to the world of model-based approaches. We apply model predictive control or time the A star to make changes. And this is the result. Now it's, at the moment it's just simulated, but we are already collecting the experiments. There were some details to fix with the camera arrangement before being able to replicate this in reality, but we can see that the robot, whenever the human makes a motion that could create collision, the robot detects this problem and works around by making a change to the plan. Okay. Finally, I would like you to show, and this, in my opinion, this is a very good example of mixture of model-based and learning-based approach, because we use learning-based approach to extract the skeleton and also to make prediction of the motion, and we use model-based techniques to execute our prediction. Our planning. The second example I would like to show has to do with ultrasound imaging, okay, so ultrasound diagnosis. So in this case, this type of diagnosis is very good because it's possible to extract a lot of useful information without interacting, without invading the human body, because we stay outside and it's perfectly safe to do this. But the problem is that it has to be well done, right? Because the data resulting from the diagnosis are highly subjective, because they depend very much on the skills of the operator. So in this case, it's a lung ultrasound, and it is important that we maneuver the probe so that we remain in the costal gaps, in the gaps between the two ribs. Otherwise, we don't acquire the correct images. We should also orient properly the machine, okay? And another thing is that we have an obvious shortage of operator that is slowing down the possibility of having this precious and important exam. And so what we can do is trying to do teleoperation, but teleoperation in a way that is guided by the system, so that we avoid problems related to the distance, and we also avoid problems related to the lack of experience of the operator. So the first thing that we do is that we have a perception pipeline. In this case, we start from a segmentation. We construct our point cloud. And based on that, we construct a model. There are very good tools based on machine learning to do this. There are very good tools also to construct models of the skeleton. And what we did is to take these two models that can be constructed by simply taking some view of the person around, and then making a procedure that fits very well one into the other. And it is interesting that the results, in terms of physiological distance of the bones that we measured afterwards, were amazingly close to the real numbers, right? And it's interesting because this type of result is completely non-invasive. But the interesting thing is that once we carry out these results, we deduce the position of the ribs. And this position of the ribs can be used as a guidance to execute the exam. And what can we do? What can we do? In our case, we use a technique in robotic that is called virtual fixture. So in essence, you have a point that is moving, you have an ideal point, and there is a control algorithm that makes it so that you don't go astray too much from the real point, from the desired point, right? And so in some sense, it is possible to guide the person so that he or she, the operator, so that he or she remains within the gaps between two ribs. Now we are experimenting even better alternatives that allow us also to control the orientation of the instrument, but this is ongoing work. And this is just an example of what we did. As you can see, we have a remote station and we have the robotic station, and then what happens is that we use the rib that we estimated to guide the exam, so that the operator succeed in following the right position in the rib cage, in between the rib cage. Okay, let me just draw some conclusions. Intelligence in robots is a fascinating and it's very challenging field. There is a bunch of new techniques that have come up, like deep learning and large language model, that allow to think what was unthinkable just a few years back. But these techniques have to be used with some grain of salt, because when we move to the robots, it's important that we make things in a guaranteed and in an explainable way. So it's inevitable that we come up with a kind of mixture of model-based and data-driven approach. So if we had to summarize in a sentence what we are doing, is that, okay, learning is important, but you don't need to learn what you know already. Right? So just concentrate the learning part on the things that you don't know, please. It's not useful at all to rediscover the wheel, right? Let's try to understand what to do with the wheel. Okay? And I think that stops my talk.
Okay. Time for questions.
Thanks, Luigi. It's very fascinating, and I think that there is one aspect of robotic that you have touched in your presentation, that is these aspects of being aware in the world. I was referring especially in the one that stops when the person is nearby, or even this last one.
Situation awareness.
Yeah, it's partially is situation awareness, but partially is the awareness that you are part of the world. So
sure.
Even when we are distracted, we don't bunch against the wall. Yeah. We are not situational aware, yeah, but we are aware that there is a wall. So it's a little bit different. In psychology, there is this idea of embodied cognition. I wonder if you think that these aspects of embodiment is something that can be applied or is applied in robotics, and how do you feel about it?
Well, it's hard to say in general. I'm just if I think I got your question, but I'm not sure.
It's not a question.
There is a theme here in which once the robot interact with the human, also the human interact with the robot. Okay, so what we didn't see in the video of the human aware motion planning is that when you take your decisions, the human behaves accordingly. We kind of pretend that everything kept going as if we were not present. There are other models in which we are working, in which we saw the closed loop interaction between human and robot. This is called, you can use game theory for that, or opinion dynamics. I have a student who is working on opinion dynamics. You create a kind of awareness of how you change the environment, and the environment is changed by you somehow.
No, that's certainly a point. My point was a little bit different, even if your aspect is very interesting. Now, my point is that in your approach, it seems to me that you try to get everything back on reasoning, or some aspect related to reasoning. Yeah. While for human beings, it's not everything about reasoning. Sometimes it's also...
small thing is about reasoning, in fact.
Yeah. And so what I wonder, is this model based on analogical response more than reasoning in logic,
so
in more or less?
You mean if we are trying to build something like an emotional aspect in robotics?
Yeah, there is this theory.
There are people who are working
that emotion has this part.
But the problem is that conflicts with the very nature of robots, because the robots are supposed to be predictable. And the only way to make a robot predictable is to make it reason. If we make it feel things, it can be nice to interact with, but not necessarily predictable. It's just a matter of setting priorities.
Okay. Anybody else? Yes.
I have a question about your knowledge base, the one you talked at the very beginning.
Yeah.
How do you update or change the knowledge base? Because it is not so easy. I mean, to me, to change the structure and include other knowledge, and without tampering on the what you already know to do, what to do, and if you add something else, maybe you can damage the overall structure. What kind of check you have to put in place?
Yeah, let's say that the advantage of having a logic-based knowledge is that it's in some sense compositional, right? When you learn new facts, you just add new predicates or theorems somehow, right, about how things are done, without necessarily impairing the rest. And it's important because this allows you, okay, when you learn things, you start doing stuff, then you encounter a situation where you didn't predict, or your robot doesn't behave as predicted. What happens is that you can transform it into a new piece of knowledge, into a new predicate. When this happens, don't do that, right? And then you mix it up with the rest, and when you generate your new plan, you incorporate these pieces. Yes, there could be a point in which things get becomes, let's say, unmanageable, because you have learned too many facts that are contradictory, and so you end up not having solution for your problem. This is a possibility, but per se, the logic nature of the knowledge base makes it upgradable with new facts.
If you want to include a task that you want to perform in a better way, so it's not just composing something else, but substitute a piece of your knowledge.
Yeah. Okay, what we did is that we have this decomposition between high-level knowledge and low-level knowledge. High-level knowledge is how you get things done in abstract terms. Low-level knowledge is how your concrete robot does it, how you can refine your actions. So it's just a matter of replacing your low-level knowledge with something different.
Any other question? So I have one question. Actually, I would like to try to make a connection with the Giovanni talk. So is there any need in robotics to explain the decision of the robot to humans in order to improve or in order to justify what they have done? So,
But you mean in real time?
Yes.
Never thought of it.
But do you think that this could be
I think
I want to kill you because I don't like it.
I think it could be okay. What we are working on is a kind of non-verbal coordination, right? In some sense, what the pose of the robot suggests what the robot is going to do, and vice versa. If the interaction becomes more complex, like with visual elements, with a piece of synthesized voice, etc., so that you can have a more sophisticated exchange on what is your intent, it's something that we haven't yet investigated. But for sure, of course, it could.
For example, when the robot has to decide which plan to use in order to achieve the goal, I guess.
I see it in a different term. So take, for instance, a collaborative task. A robot and a human collaborate to construct something. The robot is sometimes a co-worker. At the beginning, it's obvious that the human will correct it very much because it needs, and so there will be an interaction. The robot has to explain what's going to do. Then, as we move on, we start to get acquainted with each other, and then perhaps the interaction can escalate to a non-verbal level.
Providing explanation, I guess this is what Giovanni was providing before. So explanation in why that plan instead of another one.
Okay, I think it could help, but we should understand the specific application of this. not in general. There could be application where, for instance, medical application for sure.
I was thinking something like
Yeah, for medical application, giving an explanation of what is doing, because it's the same thing that the surgeon does, right? When you operate, you explain to your collaborator what you're doing and why, because in case somebody has to take over, he or she knows what
and
the
why
plan
he's
was.
doing
Yeah.
that way.
In this case, could be helpful. Yes.
Okay. Thanks again, Luigi, for
Okay.
the presentation. So now the turn of this is a co-shared presentation, Giuseppe Riccardi and Massimo Zancanaro.
Okay, so the first part of this talk, short talk, I decided to give you three insights in what the work we're doing this part of the project, and they go under the general umbrella of conversational AI. And then after this, Massimo will do his part. So what I decided to do, given also what I heard, I was told yesterday, but it's not just you, it's everybody. There are some issues in the way knowledge is transmitted over social media. So pretty much I heard a lot of companies, small companies, research labs are trying to squeeze LLMs into their product workflows, research proposal, whatsoever. And so what I'm going to tell you is about some of the finding and directions we took to investigate further and deep into how generative AI, in particular large language models, could benefit human-machine dialogue. For the rest of you, generative has not to be interpreted in the very evocative term, but actually it's a technical term transformed into a very communicative term, but actually it's autoregressive, causal, left to right, and all that. Anyway, the first question that in my group we've been addressing the last couple of years is, can we rely on large language models to manage knowledge? It's a given, and also you know that Google and others have been trying to use this as a part of their search engine and everything. So the questions that we ask in our group, and this is research led by Mahed, Musavi, and others, we ask, but what if we really try to treat the LLM as a knowledge repository? So we ask questions, we expect to have the truth, given that we know the truth, and we evaluate this. So that's what he embarked, him and the others, on this problem. And here you'll see, for instance, an example of a query on this entity, Cristiano Ronaldo, asking, what is the current team of Cristiano Ronaldo? And he looked over many, 28 state-of-the-art large language models, expecting to have either the truth or what's the best they could answer, one of the two, okay? Given that the dump they were trained on was the latest, not the latest whatsoever. So he did a very in-depth analysis about how much training data, how the training data that each of these language models could possibly give as an answer. And we found answers that, you don't want to give to your clients when you sell your LLM, whether it's a general or fine-tuned, because if you go and look the paper that he wrote and also the other ones he's working on, you'll find something you want to put under the carpet, okay? There are many things he found out, in particular the consistency of the output of large language models based on input uncertainty, meaning that you would overgenerate semantically equivalent query to get a ground truth answer. And here you'll get a plot from that paper. You'll see, although instructional models do better, still are not knowledge repository, cannot be trusted. So this is bad news. What I also did, which again I don't have the time to go into, is that there are also some other approaches I don't know if you're aware of editing knowledge in large language models. Also, they failed because most of those works are beyond academic in the sense that the data set they trained was really bogus. So don't get fooled by editing algorithm, don't get fooled by RAG or over RAG, because that's just a surrogate. So this is one important point. If you want to know more about either read the paper or stalk Mahed. Another aspect we've been working on is reasoning. Again, this is an ongoing predicate being used by marketers, technologists, researchers, unfortunately, that claim reasoning with LLMs. So we embark into figuring out what's good about this claim or what's bad. In particular, when you design human-machine dialogue system, we need to have this ability very well, strong, established, because we have to interact in a linguistic but also multimodal way with these humans, and entities start popping up as you inquiry, and we need to connect temporally, spatially, both. So, for instance, one work that we just published at EMNLP, Bruno et al., looked at even a very narrow problem, but you think this would be solved by the reasoning ability of large language models, which is just to classify through a quaternary problem whether two events were preceding or succeeding. And again, you'll find surprises there because they cannot tell very well if an event happened before or after following a passage that we passed to the large language models. Again, this is something that you can go and further get. There is a general debate, again, about this, not only the reasoning, the theory of mind. I mean, it's a nice party discussion or also a business lunch about you can do, but that's just beyond the illusion. For instance, some recent work we're doing, and we're preparing a publication, so I'm told. We're uncovering from the academic perspective that some of the issues in the claims lies in the data and how it's being annotated. And so here you'll see that the blue ones are the true, in other words, model errors, while the orange are the ones due to data annotation errors. So, I mean, if you see this, even visually, forget about the raw numbers, you're saying that your claims about reasoning makes no sense. The last point I want to make, I've been pretty much making since December 2022. The large language model is not a dialogue model. So if any of you has any confidence about what perplexity is or blur, should really go back to the original papers, what this is about, and not use to evaluate your large language model, whether it does good for search or anything. It has nothing to do, okay? And if you maybe buy in your clients, you're gonna have some trouble down the line. And so what we proposed is a contextual dialogue interaction-based human evaluation, which has multiple dimensions, takes into account the interactions, looks at all aspects of interaction which are important, both the semantic part, the discourse part, the pragmatic part, and really gives you a fuller view on what the dialogue is about, how it's going well or not. And this is a paper we published some time ago. I don't see many companies. I don't know how many people are from companies. Oh, wow. Only 2 left. Because the other aspect is that evaluation is very important. Unfortunately, in conferences lately, whether it's a AAAI or EMNLP or ACL or any other, nobody talks about evaluation. But again, when you're going to grab that customer, it's going to ask you about it. And these are recent quotes from Wall Street Journal CIOs, where they're going to do prototypes. Maybe you'll get a POC. In the end, they're going to assess return on investment. And when they're going to ask you for that, you're going to go back to research because you're going to start from research. So that's just a claim that this answer needs to be answered in research. So you start earlier than later. Thank you. And now, Massimo did the right homework because he put the presentation in.
Everybody else. Okay, thank you. I will do this last presentation, I think, so I will try to be as quick as possible. So the idea in human-computer interaction applied to AI is today that there are basically two large perspectives on which to see interaction with AI. One is the one just hinted by Giuseppe, that you are talking to an artificial companion, which is almost like a human, but not really like a human. And these are some benefits and also some drawbacks, as Giuseppe argumented. In particular, you have this aspect of social, that encourages social attribution, which sometimes can be really dangerous. The other aspect is to try to build tools, so objects, that are smarter than the normal tools. For example, the very famous Nest thermostat that has been acquired by Google for $3 billion. So there is something beyond that. This is sometimes works better, but there is a problem that there are some opaque mental model from the point of view of the user. So we are not used to work to interact with tools that have their own goals in some way. This is the first time in the history of humanity. I would like to say something about that in particular, because this is some part we work on in the FAIR projects. So one of the things we did in the project is to try to help some colleagues from the University of Bari to try to improve an interface based on classification for rhinocytology. These are nasal cells, something very obscure. But the point is that the system classifies the nasal cells according to some categories, and there is this human that has to check what the machine has done. What we have done actually is try to take this system, this interface, and try to apply a user-centered approach, trying to get an understanding working with physicians. I don't go much on that. You can see the paper there. But what we have done is try to rearrange the idea, the interface in a way that makes more clear and more familiar with the physicians to find the different places and the different aspects. This has been done, largely has been done a usability study, a standard one, but more than that, we try to apply a paradigm of classification, clarification, negotiation, and reconfiguration in a more general way. This is an aspect in which you can merge usability standard interfaces with this with a new idea of a paradigm that introduce some guidelines in order to improve this. But in general, what I want to focus today is something more peculiar, more specific than that. Is when we change from this idea of interacting with humans to this idea of interacting, which is probably less conceived for a movie in Hollywood, but it's something that for me it would be much closer to the future. I don't want to talk with my machines or something very weird. But I mean, at least conceive me that there is an opportunity also in this way. At least if you trust the $3 billion spent by Google, I think there is something beyond. So even if you do this, there is we can inherit 50 or 60 years of graphical user interfaces, and that can be used for the best. But there is also an aspect in which the form that you give to this interaction, actually the form follows the function, as the old Bauhaus motto, but also the form determines the experience, and sometimes in an unexpected way. I would like to give you a couple of examples. One will be very quick because Giovanni already introduced it, is this algorithmic recourse. Okay, so Giovanni, it's the very same algorithm that Giovanni explores and the very interface. What we did, we tried to build an interface that exactly exploit the powerfulness of their algorithm. So this idea that in a very few steps, taking very few preferences, you can immediately reach the best possible solution. And so the system proposed changes in the plan. So in this case, the idea is that you have to get a master, you have to reduce your request and increase your salary, which is reasonable, in order to get a credit. And then you can express your willingness to take this plan. Perhaps also just go into detail and say, yes, I like more this and less than that. But eventually, what you can do is just, what you have to do is just to keep the plan or ask for a new plan, okay? Because this allows the system to work in a more optimized way. And you have a mathematical proof for that. So they have a mathematical proof for that. And we try to compare this with different paradigms. The one that is used today, this is based on a paper already published, the interface. We redesigned the interface, but basically it's the same. We didn't want to make it very different for the testing purposes. So you have exactly the same plan, but when you don't like a plan, you actually are free to change whatever you want in a very explorative way. So in this case, I say, okay, I don't want to go for a master, but perhaps I can work more hours per week, and so to improve my money. So it will be this equivalent. And so if you do that, and then you ask you do your preferences, and you resubmit your plan. Of course, this is very, very inefficient. And you can prove mathematically that this cannot work, or don't work for the best. So what happened? That our users actually, just to tweak the story short, people actually recognize that the guided interaction improves the efficiency. But actually, they felt much less freedom in doing that. And this sense of freedom was frustrating. On the exploratory interface, there was more excited and provide us this sense of freedom, but actually they recognize and they say, oh, in a real life, I would probably don't do that. I mean, really a waste of time. We didn't have a statistical evidence because there was just a pilot study that the experience is different because there are too few subjects. But actually, if you look at how the time they spent on the interface correlates with user experience, in the latter, the more time they spent on the interface, more they feel frustrated. While in the first one, in the guided, more time they spend, they not impact on the perceived efficiency, but also increase attractiveness and perspicuity, so the sense of familiarity and dependability. So I think that these kind of things will prove that having the best interface can be frustrating, but when people realize it improves. So the idea is that just standard usability test cannot work here. We have to reinvent the interaction. I will give you another example about that, even probably more drastic. You know this idea of human oversight from AI Act, so the human should be there in order to be sure, to certify, let's say, the decision of AI. But this is not enough, actually. There is what I like to call the silent killer, like hypertension, is the automation bias. The idea is that people tend to take the suggestion of a computer or of machine learning, in particular when it is wrong. And so we try to do an idea of try to reverse, to combat, to fight this automation bias. And we propose a different paradigm that we call the Socrates paradigm. So the Oracle paradigm is the same one. We use a very strange task. We ask our students to classify birds. Of course, this is an impossible task for most of the students, and we actually we selected those students that did not know anything about birds. And so, of course, this was impossible, but we have an intelligent system, and this is based on an open source visual language model, large visual model. And so the system produced, let's say, a suggestion with a degree of confidence, so the probability of this thing. And then we link to the Wikipedia page. And then the user can ask for the second or the third, so up to 3 suggestions. And then, but then eventually he has to choose one. Okay? And this is the typical Oracle. You have an AI that gives you, oh, this is the answer then you confirm it. The Socrates is a little bit different. We tell the user we present the user 3 images that they can be considered most likely more similar. And for each one, we provide the least similar images in that category. Okay? Of course, as an engineer in machine learning, you realize that the system is exactly the same. Okay? It's just the interaction is presented in a different way. An oracle way, this is the answer, trust me, or not trust me, but this is the answer. The other one is I make your reasoning about looking for similar things. How do you think that this makes the difference? It's an incredible difference. So we have that the performance have an increase of 30%, very significantly with a very, very high effect size. So it goes from 0.7 to 0.9. And then we have some confusion about the time because the time is a little bit higher, but also the variance is high. So this will probably be investigated more. And we didn't have any big difference in user experience. So there is a lot, again, to study about that. But this idea of imposing a cognitive stops and reflect and helping through the interface to the system to do it, I think that this is the key for this kind of interfaces, at least for the smart tools. So in conclusion, just there are 2 main perspectives. Both will require a human-centered design and don't overestimate. We should not, underestimate the form of the interaction. So thank you.
Okay, so we have time for questions. No questions. Okay, so I think I have a question from Giuseppe and probably also for you, Massimo. The first one is about validation. So make a connection with the previous talk. So having a robotic system that, let's say, translate from the text to a knowledge base and then take a decision on the knowledge base, introduce the problem of that the robot is in the real world. So it's around us. And you mentioned about the verification, the validation of LLMs. So can you elaborate a bit more on this and actually on the possible impact on the real world that may have?
So the point about the assessment of large language models as knowledge repository is to assess whether large language models in any way learn about entities as atomic units. And our conclusion with this study was that they don't. So as in real life, this is an issue, because if we have to use large language models, for instance, for a we tried to do a collaboration with Luigi since I came here with language, spoken language, then it's a major issue because we need to ground our speech with the entities that are in an environment with not necessarily structure. So it's a very important problem, which I hope will get to a point.
Okay. Any other question? So one question from with Massimo. So from what I understood, there is also the way in which you use AI in general can make the difference. So especially when the AI has to interact with humans in the society. So you made the experiment with one user. So what about a community and of people that work or interact with AI? How the complexity can be managed in that case? Because there is
many persons interacting.
Yes,
among
I mean,
themselves and
yes.
Yeah, of course. Okay. No, of course, in that case, the complexity increases. We have the same problem of automation bias, probably, but also this idea of being aware of what happened to the others. So I think that this part of complexity.
So is there anything that also relates human to humans and then human to AI?
I think yes, human to humans take care of themselves, I think. But the idea that you should work for the AI to being aware that there is something else beyond. So if I interact with a group of other person, I have to understand what's going on with the person. There are some interesting studies, not done by me, but by other, in the literature, that, for example, in having an artificial agent interacting with a group of children to study mathematics. And so the children can work among themselves as a group, and the artificial agents in that case was just a face on the screen, but you can think of a robot. And of course, part of the problem was to model the discussion that was going around among the children. And I think that this is really, really fascinating. And of course, it's much, much more complex.
There are works on that?
Yeah, there is some work on that, on this group of users interacting with an AI. Mostly in conversational, I think, as far as I remember.
So in that case, so the AI has to take care about the multi-perspective of the problems?
No, not necessarily. I think that in that case was the case to be a coach for the children.
Yeah, but in general, I mean...
In general, probably, yes. It has to be to have a model of each one, a model of the mind of each one, and probably a model of the status of the group. So you need to model,
So a model of the group.
the groups, yes, the property of the group, who's the leader, how the interaction goes on, and so. Okay. Yeah, I think it's very fascinating, very interesting.
Thank you, both of you, for the presentation. Very interesting. So let me phrase what I think about the difference between Oracle and Socrates. I think with Socrates, you are recognizing the mistake of the model, actually. Because if the model would be perfect, the confidence would give you the right answer. So it's not really an oracle, that one. In the sense that what you do with Socrates, you are actually recognizing images that are not similar to the input, that have high confidence, while you can retrieve another image with less confidence, but is much more similar to the input. So actually what you are doing here, I think, is to recognize when the system is actually making a mistake in the prediction.
No, that's not true. So what we've done is exactly the same aspects. The confidence, okay, in this case is just a fake example, but the confidence is what the probability. So we have the higher probability first. So I think the oracle is the standard situation in this decision-making process. So the system gives its best shot, and in the best shot can be 99% confident or 80% confident. So, but it can be wrong, even with a 90% confidence. So but these are exactly the same three that you will say there, but without the confidence, but with the three presented as a similarity.
Yeah, but exactly that is the point. So if I know nothing, I will use the confidence. And so I would pick the wrong prediction as a good prediction, because the confidence is giving me the idea that that is the right. But on the other side, on the Socrates, since you can compare the images, then you can recognize if the prediction that was getting the highest confidence is actually wrong.
Yes, it could be, but for the data is not always the case. There are cases in which the confidence is very high, but the images does not look exactly like that, and so people will look at the.
So then it will be interesting to see how correlates. I mean, or how the improvement correlates with the error.
Yes, if I remember, I have to check better the data, but if I remember well, since we manipulated this data, it's not always the same. But yes, you're right. This is something that I have to
just to
argument.
continue the discussion. It's not like the confidence in that case is given by the system, right? But by the AI.
Yes.
And in that case, it's a human confidence that you are selecting. So you give the freedom to the humans to say, okay, for me this is closer to the.
Yes, but still the point is that if you. But my point was not. I mean, it is on the form of interaction. But the point is that the form of interaction can change the performance.
Yeah.
This is the point.
That was clear. Yeah. Okay. Thanks.
Giovanni.
Who was first?
Okay, it seems to me that in the last years, some work has been done to make, as you were asking me before, to make a system, AI system more human-like, even more emotional, fallible, right? You know, providing you explanation is a kind of display of insecurity somehow, right? I'm not sure, so let's work together in order to encourage collaboration. But these human traits, when when you are in front of a computer, are not intimidating because you use your imagination and you can think of whatever you want beyond the screen, right? In some sense. And so you can, but when you have to do with something physical, and as you were saying, we are used to think of physical things as tools, as extensions of our will, right? Perhaps showing this type of weakness could deteriorate the ability to really collaborate. Because in this case, you see something physical, you want it to be deterministic, etc., because you cannot use your imagination. It's out there, right? You know what it is, you know how it moves. Can you elaborate on that?
Yeah, it's very general. I agree. I think that basically I agree. I'm not sure how far we can go on that, but the point is that there is a lot of evidence that having the system look like a human being as much as possible, for example, using natural language, using manipulation, to some extent can be useful, at least in some tasks. In other tasks can be annoying, in other tasks can be weird, and in other tasks can be even detrimental. On the other side, having intelligent objects in some cases can be very familiar. For example, in case of Nest, the thermostat, it's very, very nice. You can set it, and then it learns the habits of your family, and in a few days, it set himself. It's wonderful, but the point is that if something changes in your house, you have to fight with these things that change on themselves. Okay? And so I don't think that there is one is better and the other is worse. It depends on the specific application, the one or the other. But then when we go to the smart tools, we have to reinvent a way to use the tools. Because again, we are not used to tools that do things on themselves. If I switch off the light and the light does not switch off, there is something wrong. For me, there is something wrong in the switcher. There is not something intelligent behind it. But it could be in the future that actually there is something that for some reason the house decided not to switch off. And so how can we better communicate these aspects? We work a little bit on this aspect of decision making that is partially different, but and what is not my assumption, I think the assumption generally in HCI today, that the form in which you build your interaction can drastically change the performance, even if the background is the same. So you might be correct that we are suggesting the wrong, but that's exactly the point. Even if it is true, that's exactly the point. The point is that we have to improve our models, our machine learning, our large language model, as much as we can. But then we have to to give a reasonable amount of research also on the way we present, the way we shape the interaction. Okay, these are just trivial and simple examples. And so in some sense, I agree. Explainability, and again, there is a lot of research, is great in some cases, is completely useless in other, and is even detrimental in other, again. In our study with the doctors, again, that was a pilot study, but some of the physicians tell us, I don't want to see any explanation by the system. Who cares? I mean, I'm the doctor. I take the decision. If the system is wrong, I will change the system. I don't want to wait to read explanations. Yeah, no, I agree. I say that some of them tell us that. Others are not telling that. You're right. It was just an anecdote. It's not a scientific proof.
Very simple question. A yes or no question. Like here in the confidence of the AI, are these confidence like calibrated, or they are just like the output of the model? I mean, we can follow up later. I mean,
in our demo, I think that they are just the output. In the user test, we actually we manipulated in order to have the same amount of possible error and things. So when we presented it to the user, we faked the data in order to have the complexity of the two tasks.
So they're not like really the true output of the model?
Not in the user test. In our demo, I think we actually take the probability, not calibrated. Okay. But when we do the user test, we wanted to show some very easy example. When we can recognize the bird and the confidence is high. Some example in which you can recognize that the confidence is a little bit lower. Some example in which you don't recognize, so all the possibility, and to have the same calibration on the other side. So we couldn't actually rely on the machine learning to have both tasks the same difficulty.
Okay, thank you.
I understand your point, but this does not apply to the test. In a real system, that should be, of course, very relevant.
Okay. There is any other comment, question? Let's thank again Massimo and so these two talk close the session, and actually we are at the end of the workshop. Paolo has just arrived for the conclusion. Let me say that actually in this session we saw something very interesting stuff, and I think this will be also increasing the interest when AI has to interact with humans. I think this will have a strong impact on our daily life, and this is something that we should care about. And if the research go in this direction, I think it will be very, very, very interesting. Let me say something about to close, and then I leave you to the final conclusion. So we started the introduction this day. I was the one that was showing the KPIs, and we say that we are doing quite well and actually impressive about the numbers with respect to the targets that we had. But actually in this 1 day and a half, we saw a lot of very interesting stuff. And actually the debate also was during the session demonstrate that there is a lot of things that is going on. So we have still 1 year, no, right, Paolo, more or less, to conclude the project. I'm really, really interested to see what we will have at the end, and actually the future work that will be more interesting as well. Okay, thanks everybody to have been here, and thanks for all the presentation. And just leave Paolo for the final word to conclude.
No, yeah, thank you very much. I'd like also to thank you all, to thank the university that presented this morning. They are really making our partnership much stronger. To thank, of course, also the company that yesterday had a very interesting discussion about the role in the market. To thank the excellent young researcher that presented, like Giuseppe Riccardi today. And no, we have several younger researchers, and thank you very much for everything. And of course, the third year will be the most interesting, because we will have a much larger partnership working with you all to have a big success. Thank you very much. Thank you.